Hello everyone, and welcome to our second and final webinar in our Motor-CAD series. Here we will shift from the motor level to a system level perspective. But before we start, let me introduce myself first. My name is Lisa Sitar. I'm a marketing officer at Infinite Simulation Systems and a moderator of this event. Before we start for real, I'm gonna share some short instructions with you. So first of all, please note that this webinar is being recorded and the recording will be shared with you afterward. Secondly, you cannot unmute yourself during the webinar. However, I would really like to encourage you to still ask questions, and you can do so by writing the question down under the Q&A section. You can also see on your screen, and all the answers will be then provided together with the recording after the webinar. Okay, so let me introduce our speakers for today. I'm joined by my colleague, application engineer Shashank, who you might already met if you joined our first webinar. And this time we also invited engineer Tuhin from Electric Superbike 20, who will share actual example of how their team used Motor-CAD in their racing project. So, Shashank, please, the word is yours.
Thank you, Tisa. Let me start here. And yeah, good morning, everyone. So my name is Shashank Shanberg, and I'm an application engineer here at Infinite Simulation Systems. And I work on electromagnetic solutions such as Motor-CAD and Maxwell. You might have already seen me explain a bit about Motor-CAD in the previous webinar. But today I'll walk you through today's session on system-ready electric machines using Motor-CAD. Let's see the agenda for today. So we'll start by revisiting our previous webinar just to have a brief outlook, and then we'll see what's the need for system-level simulation, what we are using to do the system-level simulation. So we use functional mockup interface, how there are different functional mockup units available in Motor-CAD, how we can integrate Motor-CAD with Twin Builder, and finally we'll end today's session with a real-world case study by Electric Superbike 20 team. And let's get started. So you might have seen this previously, but let's go through it again. So we, in the first webinar session, we saw the workflow of Motor-CAD and how to design a machine and how all physics models shown here can be tested together. You don't have to move to different softwares, let's say, to check each of these physics models and physics interactions in the motor. But here, like you can see, the arrows represent the transfer of data between Motor-CAD and also the multiphysics interaction within the motor itself. And this is very critical in multiphysics simulations and also system simulations. So each of these models can be used on their own, but also together. For example, you have the electromagnetic module and the lab module. Now, both modules can be used on their own, but we can see that they interact by passing information on the current, speed, phase advance, as well as the losses and fluxes. And all these can be related to each other with different parameters. In the thermal model, we can see how you can use different cooling methods available for machine, check temperatures between interfaces of the machine, and the heat transfer across air gaps as it's strongly speed and temperature dependent. There is also the mechanical module in the Motor-CAD where you can check magnetic forces and current data as inputs, and it provides the NVH analysis and gives us an idea whether the speed is mechanically achievable or not. So we established the following key takeaways from our last session about Motor-CAD. So we saw that it's very easy to use. There are quick iterations that you can do. Multi-physics simulations are possible, and this acts as a rapid and accurate solution for before moving on to a detailed design, let's say. And you can go to our different solutions like Fluent or Mechanical, Ansys Maxwell, OptiSlang, and like the one we are looking at today, Twin Builder, for the system level simulations. If we start our motor design, so let's say we always start with the RFQ level where it begins with some specifications. And once we are given the specifications, we then move on to the concept design stage and then the optimization stage. which utilizes a range of physical domains. Like you can see the electromagnetic, mechanical, thermal, and electrical simulations. And only by considering all of these together and performing multiphysics design, we can be sure to create a well-optimized model across the full operating range of the machine, and one that meets the specifications and performs as well as part of our complete system. So we know that in electric machines, there are increasing demands of high efficiency, high power density, low cost for electric powertrains, and that has led to more closely integrated systems and solutions. So small packages, shared cooling between the power electronic components and the electric machines. And so it becomes more and more important that the other components in the system are analyzed along with the machine itself, so that the evaluation of the system is something that needs to be done throughout the development process by looking at each individual component performance, and then looking how those fit in a overall like subsystem and get top level view. Also, the constant cost reductions and efficiency improvements required for shorter development cycles, consideration of NVH and reliability issues, all coupled with increased integration of electric machine within a complete system. We know that when we look at the overall system level optimization, you know that individually optimized motor, inverter, or transmission doesn't necessarily mean that it's an optimized system, and it's very important to consider this throughout the design process. So for an e-machine, we look at some of the components. So we often combine the machine design with these components, things like inverter and transmission, the control systems, battery in case of a vehicle, and cooling, which is sometimes shared between the components. We model those multiphysics interactions between the components, and for that we need reduced order models, which run fast within the system simulation environment, where we have multiple components, and we need to make sure that we maintain sufficient accuracy for meaningful results, and we need to make sure that it's really accurate. So from a product development cycle, you can see on the left side of this chart here, we start from some initial design topology, design optimization, and then we go on to detailed physics-based design. And then we move on to the right side, where we look at how this integrates into a larger system, checking at the system level we are still meeting the requirements or not, and performing other tests to sort of validate and verify the overall performance. For the system level co-simulation, let's look at the functional mockup interface, which is a standardized approach for coupling models. And in particular, with Ansys Motor-CAD, we have different models which can be very useful for electric machines. These are the functional mockup units, which is a term used for the individual components inside the interface. Here you can see a co-simulation of Ansys Motor-CAD, in particular running the lab module of Motor-CAD along with the thermal module in a system simulation setup on Twin Builder. So the interface that you're looking at is the Ansys Electronics desktop GUI, within which you can co-simulate the FMUs. This is very easy to use because we can bring in the FMU block, refer it to the Motor-CAD file that we designed, and then connect it to other components and get going with the system simulations. These are available FMUs here. So you can see the lab FMU, the thermal FMU, and the custom FMU. So the lab FMU is currently only available for brushless permanent magnet induction, brushless permanent magnet and induction machine, and also synchronous machine types. So we can include things such as variable speed. We have detailed thermal model, so variable resistances, accurate mapping of efficiency maps and losses, for example. And also we can see that Twin Builder is very useful in sensitivity analysis for parameter sweeps and optimization as well, and it can be easily coupled with different components in your overall system. As we saw the different available FMUs in the Motor-CAD, so let's look at them one by one. So here you can see the lab FMU. The lab model files can be exported from Motor-CAD and then imported onto Twin Builder. And this includes the information of the saturation maps, the loss maps, we can use these parameters in system simulation, and this is using analytical model, but derived from the 2D FEA transient simulation of MotorCAD. So we can specify torque and speed demand, and then let the lab module determine optimal control, or we can specify, let's say, current and speed, or even current and phase advance. So there are a few different options available. For example, temperature effects are included. That is how things like flux linkages change the temperature. We can consider magnet, air gap, or bearing temperature of the machine. And this is important in calculating the optimal operating points with different DC bus voltages as well. As you can see, the output blocks, we can get the voltage, current, efficiency, and the power factors. And we can also check the achieved torque and power, and also various losses in the individual components. Here, for example, we can import a template from permanent magnet machine from MotorCAD. And once you open the template component inside the Twin Builder environment, and it opens a window that asks for the path of the lab file. And the important thing here worth mentioning is that once you export the lab model, you do not need to have the MotorCAD license anymore. You can use the solver that is exported with the MotorCAD inside this FMU. So the license is released there. So here we can see the other FMU, that is the thermal FMU, in a coupled scenario. So this is actually running a lumped parameter thermal model, and you can see this is a co-simulation method that's running the thermal transient, and also it's been designed to work together with the lab FMU. So with the two together, we are able to calculate losses, put them into a thermal model of the machine, and run transient data cycles in a system simulation. And we can connect those with other components and look at top-level system performance. So to integrate your MotorCAD thermal model into Twin Builder, generally lumped parameter thermal network is used and formulated as set of matrices. And MotorCAD already provides the capability to export these, allowing a thermal model to be created within Twin Builder. The major limitation, though, is that the exported model is only accurate at single speed and temperature. So therefore, MotorCAD thermal reduced order model component in Twin Builder allows for creation of MotorCAD thermal model that is valid at a range of operating points. This also means that it needs quite a lot of thermal data from a range of speeds to be generated, which can be quite complex, as you know. So, however, it can be easily done with the workflow that is already documented with a Python script that is available on Ansys website. You can see the link here for that. And the complete script is available, which will set it up for you, and there is very little modification necessary. All you need to do is specify a MotorCAD model, for example, the speeds, the air gap, temperatures, and the housing temperatures of interest. Then you can just run the script, and it will automatically launch MotorCAD in the background and perform all the required calculations. It will then automatically save the outputs from MotorCAD in required formats, and it will take a few minutes to run depending on how many operating points you select, as it performs the iteration for each required combination. And important to note here is that it's not exporting the temperatures from MotorCAD model. Instead, it is exporting the underlying thermal resistance matrix, which is used to determine the heat transfer between components of the motor. As a result, the generated model in Twin Builder is computing the temperatures by actually solving the underlying model, and doesn't just simply interpolate between temperature values. This is what gives us the accuracy. You can now easily use the generated outputs described earlier from Ansys script and input that into Twin Builder, which will then generate thermal model for you. You can then select the input and output that you need. For example, here you can see the input speed and losses, and then the output will be the temperature at different locations of the machine. So we also have the option for custom parameters. For, let's say, if in case you can use this with the lab module and the thermal FMU module. So this is especially useful in case where there are parameters that you want to add, or there are some things that you wish to simulate, but that's not available in the available FMUs. And you can have 15 inputs and up to 15 outputs for this custom parameter. So you can use them together with the other FMUs and add your necessary parameters. So let's look at equivalent circuit extraction. So while you simulate a full 2D or 3D FEA machine model that is highly accurate, it's always computationally heavy and too slow to run inside a large-scale system simulation. Example, let's say alongside a power electronic drives, complex control loops, or thermal networks. The ECE model replaces that complex magnetic FEA with a mathematically equivalent circuit block that executes in a fraction of time. So for each current sweep value and rotor position, the FEA simulation is performed and the phase flux linkage and torque are calculated. The lookup tables are built from these results and that can be used in the system simulator. The ECE generates an SML model, which can be imported into the Twin Builder environment. So in Ansys Twin Builder, an SML or system modeling language is a specialized behavioral model file format. It's used to define and import custom dynamic components, mathematical equations, and structural component descriptions into system level simulator. So this can be used along with the inverter controller to evaluate and optimize control strategy, among the other things. And it utilizes the Ansys script to generate the required data. So for dynamic model integration, for bringing in the EMAG into the lab module, as previously mentioned, you can make use of the Python script provided in the PyAnsys web page and extract the SML file to easily integrate it into the Twin Builder environment. And this example shown here is based on a dynamic nonlinear DQ model. And it can be used to connect to the inverter and battery and also mechanical load and look at the transient behavior and dynamics of the electric machine. So we now saw different ways of bringing in the data from Ansys Motor-CAD into Twin Builder from, let's say, the lab FMU for performance maps, electromagnetics through the dynamic model, and the thermal model integration. And now let's look at a demo for analysis of an electric machine over a driving cycle. So losses are calculated in the lab module and they go into the thermal model, and the temperatures will be sent back to the lab module in this case. And the lab model can also calculate current, voltage, and efficiency performance. And also here we are using the drive cycle that's US06. Let's look at the demo now. For Ansys Motor-CAD integration, so here we are using the drive cycle example previously mentioned, and you can see we have two components here. So that is the lab model and one is Motor-CAD thermal model. So the thermal model on the right has some inputs that are you can see are all the loss components that come from the Motor-CAD lab module. So you can see those two are coupled together here in the electronics desktop GUI. And we also input speed because the thermal model is speed dependent, thermal model here in this case. And the output of the thermal model will be temperature at different locations of the machine. Some of this output are fed to the lab model for calculation of the machine performance. In this case, we used stator winding temperature, magnet, and bearing temperature. So we also used two different tables that you can see on the top. So tables, yeah. So driving cycle for the driving cycles and the speed and torque are mentioned there. Also, we use the input for DC bus voltage here. So this particular example is a time transient example, and you can see that in this particular GUI you have different graphs available. So these are different results that you can plot. On the top right we have the different temperatures, and then on the top left we have the driving cycle. On the bottom left we have performance of the machine, and on the bottom right we have loss components. So this analysis is set up for 600 seconds. So you can see that variable time step is used with minimum and maximum time values. So we can use based on whichever value you want. You can add this here, and then let's say you uh, analyze this. So once the analysis is started, you can see at the bottom there's an option to show the progress. You can look at the progress here in the progress bar, and as you can see, some of the results are shown here, which means that the simulation has started and produced some results. The simulation will take some minutes to complete. So by that time, you can already see the results that are showing up. If we wait for some time, we can then look at the results. So yeah, the simulation is now complete and all the results are available to look at. And if you want to, let's say, not just have these results, but want to look at more than these results, then you can create your own results from the results section shown here. And that's all from this demo for now. So yeah, what did we see? So we saw that Ansys Motor-CAD allows for rapid, accurate multiphysics analysis, and you can analyze the full design space as you wish. And this is very useful because there are multiphysics interactions involved in the machines, and the system level simulation with the twin builder environment is really easy to use. And here we saw the functional mockup interface as well, which can be used to bring higher quality reduced order models into fast simulation environment. And we saw different lab and thermal FMUs, so how it can be used. We also saw the equivalent circuit extraction, how that's used for bringing in the electromagnetic part of the MotorCAD model. And also we saw thermal model export and how you can use Python and PyAnsys to bring that in into the model and simulate your design. So thank you. That's all from my side. And now let's look at how the electric superbike team from Twente leverage MotorCAD to analyze their electric motor. Over to you, Tuan.
Morning, everyone. I'm Tuhin Shinde, a chassis engineer at Electric Superbike Winter, and today I'm going to show you how we use MotorCAD to optimize our electric motor. So a little bit about ourselves first. We are a student team from University of Twente, and we were founded in 2017. We specialize in designing, building, and racing electric motorcycles. We are also the first Dutch team participating in an international competition called Motor Student. A few of our achievements: we came first place in competition twice. And last year, we also won Rookie of the Year award at Motor Student during our debut. Now, but what is Motor Student? It is a competition held at Motorland Argonne with around 40 plus competitors from around the world. It consists of rigorous testing of the bike to make sure it's safe on the track, and then it's qualifying to see if the bike is fast enough for racing, and then finally a pure wheel-to-wheel MotoGP style racing. Now, the electromotor is provided to us by the competition. So if all teams get the same electromotor, how exactly can we get an advantage? Of course, you could try to reduce the weight of the bike. You could also try to improve the aerodynamics. But another method is to optimize the electromotor. Well, the electromotor that we get is from a specific manufacturer with specific ratings, say a maximum of 6,000 RPM, but those are based on predefined operating conditions, and the actual capability depends on the available thermal margin. And so effective cooling can increase its duration, for which higher power levels can be sustained. And with this, MotorCard helps us to quantify this available thermal headroom through simulations. A lot of teams try this. I'm not sure with MotorCard or not, but they don't do it properly and they often end up ruining the electromotor. However, I think this software helps us really, is quite helpful for us to get the actual temperature ranges for the electromotor so we can push it while not causing any damage to critical components. So let's dive into the technical details of our bike. The cooling system. So we use a different cooling system than the rest of the bikes. We use an ice water reservoir that is used to absorb heat generated by the electromotor. The coolant circulates through the motor channels, removing heat away from these critical components and takes it back to the cooling tank, where heat transfer occurs between this heated water and the ice in the cooling tank via a copper pipe. Melting ice provides a thermal buffer, maintaining low coolant temperatures during high power operations. But since onboard ice capacity is limited, efficient thermal management is essential to maximize cooling duration and prevent thermal derating. And then finally, the problem statement. High performance racing conditions generate significant heat, as mentioned earlier, and rising temperatures can lead to thermal derating. So, why is thermal derating bad? Since it's used to protect critical components. Well, it reduces the available power and torque of the bike, thus making us slow on the track. And along with limited cooling capacity, we need the cooling to work efficiently. Physical testing, of course, provides insight into the thermal behavior, but then this insight is quite limited and you might end up damaging your electromotor. So how exactly can you predict the motor temperatures and prevent thermal derating while maximizing performance throughout the race and protecting your electromotor? That's where MotorCAD comes in. So we create a digital twin of the competition electromotor and simulate thermal behavior on it. We also try to identify thermal hotspots and generate efficiency maps through the lab module. And then we optimize our cooling strategy and operating conditions through it. So this is sort of the workflow that we follow. We first find the motor geometry based on technical drawings. Since we are not legally allowed to open the electromotor, we need to find these values from the drawings available. And then we also find the amount of copper windings using resistance and inductance. Then finally, what we do is we define the operating conditions, so the DC bus voltage and the peak current and even the RPM. And then we run an electromagnetic simulation, after which we get a certain torque value. And then we compare that torque value to the data sheet provided to us by the company. And then we try to match it at that RPM. If it's similar or identical, then we move on to thermal coupling, where basically make the thermal model of the electromotor, input the flow rate, input the temperature of the flow of the coolant, and then we simulate transient heating. So after the first results are in, we try to see if these are within the cooling limits. Let's say if your copper pipe heats up to 800 degrees Celsius, you know that that is not the case and there's something wrong in the model. So you go back and you start again with the motor geometry. However, if these are acceptable limits, then we start validating it with the data we have from our last generation superbike. And then we compare the electromotor temperature and the simulated temperature. If it is consistent, then we start integrating a new cooling system in MotorCAD itself and analyze the results. If not, then we again have to go back and check the motor geometry. And then finally, the results. Well, at the moment for us, the geometry parameters are set and model verification is in process based on old data sets. As you can see on the right, a schematic of the thermal model is visible, but we are not quite satisfied with this result yet. So we're going to go back to the geometry and try to fix it. We are in contact with other teams from Motor Student and even a professor at University of Twente who's helping us out with this, and we aspire to finish this by the end of this month. That was all for me. Thank you.
Okay, thank you, Tuhin. I'm gonna share before we say goodbye just a few more details on our training opportunities. So just a reminder that in case you would like to learn how to use MotorCAD or any other Ansys solution in practice, you can scan the QR code on your right and you'll be referred to our website where you can fill out the form, our contact form, and we'll come back to you as soon as possible. If you have any other, maybe more generic questions, then feel free to scan the QR code on your left, and your question will be then sent to our engineer Shashank, who you already met during this webinar, and he'll be more than happy to support you further. So that's everything also from my side. Thanks again, everyone, to join. I hope you enjoyed the session. And yeah, I wish you a great day.